Hello, ElixirConf. Our next talk is called The Upside Down Dimension of Elixir, an introduction to metaprogramming by Nicholas Henry. Nicholas, the broadcast now belongs to you.
Thank you, Anna. Welcome, everybody. Today, I'm introducing you to metaprogramming in Elixir, and I'd like to start off asking 3 questions. Are you tired of having to write the same boilerplate code in multiple modules? Do you wish you could program in a language that more closely reflected the domain you are working in? Is there a feature you wish existed in the Elixir language? Well, open the gate into the upside down dimension that is metaprogramming in Elixir. Metaprogramming is a tool that gives you superpowers like a mind flayer. Metaprogramming allows you to write code that generates code. Metaprogramming gives you the power to remove boilerplate code, as the Phoenix generator does when it creates a web module used by your controllers, views, channels, and router. It removes multiple imports and aliases that would otherwise be repeated in these modules. Metaprogramming gives you the power to write your own domain-specific language. This example of an HTML DSL provides a relatable syntax for writing markup in Elixir. Metaprogramming gives you the power to add new syntax to the language as a first-class member. So if you're feeling particularly evil, you can add a wildlet expression to Elixir. My goal today is to demystify metaprogramming and help build a mental model of the core concepts to write code that generates code. At the end of the presentation, I hope you'll have the foundation to read and write basic macros. So my approach today will be demoing the requirements for a simple macro. We're going to learn the key concepts of metaprogramming. We're going to demo those concepts. They'll be emulated just to fit into the time constraints today. And we'll have multiple points of review to reinforce those concepts. And then at the end of this presentation, we're going to go ahead and implement that macro. This demo, you could consider the hello world of metaprogramming. It's not original, but it's a great example. And we have a calculator module in our demo that adds 2 numbers together, and a tracer module that contains a macro that will print the expression that we pass to it and return the value. The neat thing about this demo is that you could not perform this with a normal function. You have to use a macro to meet these requirements. So let's have a look at the code here. We have as explained, we have a calculator module, and you'll see on line 4, we're defining our add function. Now on line 5, you'll see our trace macro that we're invoking and passing the x plus y expression. You also notice we'll have our tracer module there as well. We define a macro on line 3, but on line 4, there's no implementation. And that's what we're going to be writing at the end of this presentation. So just to kind of see how that all works, we're going to have a look at this at the REPL, and we're going to go ahead and add 2 numbers together. And when we invoke that, you can see that we get this expression running x plus y returns 3. So that's the expression that we're passing to the macro and the result. Just to get a little bit of a better feel for how that's working, let's just set up bind a couple of vars here. And we're going to require our tracer macro. I'm going to invoke this macro at the command line just to sort of see how that's working. And again, you can see that we have our message that's being printed to standard out with the expression and the result. There are 3 keys required to start your adventure in metaprogramming. And we'll explore these through the demo. And I believe that these 3 keywords would take you far in writing your own macros. We have def macro, quote, and unquote. In Elixir, I kind of like to think that there's these 2 realities. We have a human world and an upside down dimension. Our human world, we're writing business logic that gets executed at runtime. And we write in our high-level syntax of Elixir that we love, and we define our business logic and functions. But in the upside down dimension, we're involved in code generation. And rather than programming at runtime, we're programming for compile time. And there's this internal data structure that's involved in metaprogramming beyond the high-level syntax that we're used to working in. And rather than writing functions, we write macros. And so these three comparisons here will actually form the three parts of this presentation. So let's get started on the first comparison of runtime and compile time. So and through the software development process, there's these two instances of runtime and compile time. In runtime, you're running an executable. You'll experience exceptions caused by state. For example, you've probably seen the undefined function error when you're using the not dot notation on a nil type when a struct was expected. And then in compile time, we convert code to an executable. And our compile time errors are formed by invalid syntax. So let's have a look at this compilation process in the context of Elixir. We have our Elixir source code that gets sent to a compiler, and we generate the bytecode, and that gets executed on the Erlang VM. And so sort of, in terms of our calculator, we have a calculator source file, and that contains macros. And those macros are invoked at compile time generating code. And then we have our beam file that gets executed. Okay, so it's time for our first demo. It's a simple one. We're just going to demonstrate that code can be executed at compile time. And compile time is sort of static by nature, where runtime is more dynamic. So we've got a modified calculator module here. And on line 2, you can see that we're setting a timestamp, a module attribute timestamp. And on line 4, we're going to be outputting when we compile the code to standard out with that timestamp. Line 6, we're defining our function, and on line 7, we're going to be printing to standard out again, and we're going to be specifying the compile time timestamp again, but on line 8, we're going to be executing the timestamp when we invoke the function. So what does this look in the REPL? We're going to compile our source code, and when we invoke that, we see our message on line that we defined on line 4. So we've got a timestamp there. Okay, that's great. So let's invoke our add function. And when we invoke that, you'll see that the compiled at timestamp is exactly the same as when we compiled it. And then with runtime, we have a slightly different timestamp. So just a review, we have at runtime, we're executing code. You can see it's more dynamic by nature. And we're executing bytecode. But at compile time, well, we're also actually executing code, but it's more static by nature. And here we're generating bytecode. And that leads us to part 2. So let's come back to the compilation process. So as I said before, we have our Elixir source code that gets compiled into bytecode. But it's a little bit more complex than that. That Elixir source code actually gets passed to an internal data structure. This is a representation of our Elixir expressions. And from that, we'll generate the bytecode. And this brings us to our first key, quote, which will reveal this internal data structure for us. So for the demo, we'll have a look at quote, and we'll explore this representation of our Elixir expressions. All right, so we're back at the REPL for our first demo, and we're going to pass a simple mathematical expression to quote, 1 + 2, and when we execute that, you'll see that we get this internal data structure. So you'll kind of see through the color coding that we got the addition sign at the front there in the first element, and some the arguments at the end there. Before digging deeper into this, let's just think about what this expression is. So 1 + 2, this addition sign is really an infix operator. So a traditional function call would look like this, where we have the function name first and our arguments that we're passing afterwards. But this is not valid syntax for Elixir, but we can call this on the kernel module, and that's valid. So let's come back to that first example of our expression that we're passing to a block as quote. And if we break that down, you'll see the first element is actually the actual function call. We have some metadata and as the second element. And then for the third element in the tuple, we have a list of arguments. And this is known as an abstract syntax tree. And in the Elixir documentation, you'll see it referenced as macro.t. Let's explore this concept of an AST a little further. So I'm going into a more detailed, well, slightly more complex mathematical expression there. You can see the parentheses just to communicate the order of precedence. And when we execute that, we get a more complicated data structure. I've removed the metadata here just to sort of simplify that so you can match up the color coding a little easier. Now, let's just sort of step through this. So this is a tree structure, and we're executing the leaf node first. So here we're multiplying 2 times 3 equals 6. In the parent node, we are doing our second step of 1 plus 6 equals 7. And then finally, our third step, we take 7 minus 4 and we get 3. So this concept of abstract, it's really, we only have the essential elements, and this is sort of optimized for the machine to generate the bytecode. But you can see that there's no brackets or anything like this in this AST. It's syntax because it contains the expressions, our statements that we've put in the source code. And it's a tree because it's a nested set of nodes implemented with tuples. All right, so that's part 2. And so now we know that quote generates an internal data structure that's referred to as an abstract syntax tree. And we know this internal data structure is a 3-element tuple with functions and metadata and args. And if you look at the docs, it's referred to as macro T. Okay, so this leads us to our third part of this talk. And this brings us to explore the def macro keyword. So to understand macros, it's probably helpful to actually compare them with functions. So with functions, we define them using def. They accept a term or multiple terms and returns a term. They're invoked at runtime. And when we're dealing with functions, we only really need to worry about the current context. Now, with def macro, we accept a subset of the term known as the macro type, and we return a macro type. And rather than being invoked at runtime, macros are invoked at compile time. And rather than worrying about just the current context, we've got to worry about the macro context and the caller context. So let's come back to the compilation process again. Before, we talked about having this parser that will create this AST structure for us. But it's a little bit more complicated than that, where we have an expansion component to our compilation process. So the initial parser will create an AST, but that will reference the macros. And we need to expand that, and well, the compiler does for us, and that will expand that, generating the code that our macro, by invoking our macros. So a very simple example here in this diagram, you can see our trace macro, and the AST it generates might reference and inspect. So you can think of expansion, taking an AST of macros and then transforming it to an AST with our generated code. All right, So let's look at another demo. Here we're going to look at macros and that they accept an AST. We're going to look at macros, the fact that they're invoked at compile time. We'll look at this context and then this idea of expansion. So we're going to start off with looking at the AST. We have a module here, the tracer module. We've modified it a wee bit where we're going to output a message inspecting the AST at compile time. So let's invoke that at the REPL. Again, we're just going to pass a simple expression there. And whoops, oh, we got an error. You must require the tracer module before invoking it. And you might have seen this when you've used Ecto Query or the logger, because those are implemented using macros. And so that's why we'll need to require our tracer module, because we have a compile time dependency there. So we need to make sure that the tracer module is compiled before we invoke it. All right, now that we've required it, we'll invoke the macro again. And you'll see the message printed to standard out that we have this internal data structure, this 3-element tuple. And I've, again, just removed the metadata there just to keep it simple. And you can see through the color coding that our function sign, the addition sign is the first element, and we have the args in the last element. Okay, so now we know that a macro accepts an AST. Now we're going to demonstrate that macros invoked at compile time. So we're going to compile our calculator module, our file. And when we invoke that in the REPL, you can see the inspect message that we have on line 3 in the macro. We're outputting that. And you can see, again, this internal data structure. So again, when we compile our file, macros are invoked. And of course, when we call our add function, we get our runtime value of 3. All right, so the macro and the caller context. So on line 3, you can see that we're using dunder module, double under module. And we're going to display that that's the macro context at compile time. And within the quote on line 7, you can see another message being outputted. And that's, again, using dunder module. And that will be displayed at runtime. And within the quote, that will be the caller context. And of course, in our calculator function module, and on line 4, we define add. On line 5, we have invoking our trace macro. Okay, so we're going to recompile our calculator. And when we do that, you will see that we get our macro, our message printed standard out. And the double under module is in fact tracer. When we invoke our add function at runtime, you will see that the context is calculator. So the caller context is the caller of the macro, again, in this case, calculator. Okay, so here we're going to look at macro expansion. And again, we've got our tracer module, and we're going to be outputting a compile time message on line 3. And on line 7, we're going to be outputting our runtime message. So we'll require tracer. And here we're going to emulate this passing phase and the expansion phase. And here we're going to create an AST containing the macro. So remember, the parser will give us an AST with the reference to the macro. And here you can see that. A little bit of color coding there helps with matching the macro call and the mathematical expression. Okay, now we're going to emulate the expansion phase. And with macro expand, this will emulate this expansion. And we're passing the AST that we set up previously to that. And when we invoke that, you can see, of course, we've got our compile time message So that was invoked, but also you can see with the color coding here that we have our IO inspect and the caller context at runtime string that we want to output at runtime. So we can see our initial AST with the trace macro, and then when we expand that, you can see the generated AST, our generated code. So let's do a review here. So again, when we're defining functions, we'll use def. They'll accept multiple terms and return a term. These are invoked at runtime. And for the current, we only have to consider the current context. With def macro, we use that for defining macros. And that accepts a subtype, I guess, in terms of terms. It's the macro T, which is the type of the AST. And these are invoked at compile time, and there's a consideration of the macro and the caller context. Okay, so now we're ready to implement the tracer. But before we do that, there's one more key, our final key that we need to look at, and that's unquote. Now, unquote constructs the AST dynamically, and you can think of it almost as string interpolation for your code. So let's take a quick look at that. Okay, so we're back at our REPL. We're going to create a simple expression, x plus 2, and we're going to pass that to the quote. And no surprise, we get to see the AST. This should start to feel a little familiar by now, I hope. And you can see the reference to our X var. Now, I again removed the metadata just to sort of keep this simple. So we're going to set up a couple, we're going to bind 1 to X. And we're going to execute our quote again to see what happens with X. Oh, okay, nothing. So that's sort of demonstrating that variables code outside of the quote context will not pollute the AST. But there are times when you want to be able to generate an AST dynamically. And that's where unquote comes in. And again, you can kind of consider this string interpolation for code. So here you can see we're unquoting X, and in the comment there, I'm kind of doing a string interpolation of that. Okay, so when we invoke that at the REPL, you can see our internal data structure, and now our X has been replaced by 1. And that shows us that we can dynamically create an AST. Okay, so let's come back to our demo and write our macro. So for the calculator module, now you can see why we're requiring tracer, because it's a compile time dependency, and we need to make sure that's compiled. And on line 5, you can see that we're invoking the macro. And now we know that that's going to be invoked at compile time, and that will return the AST when it's expanded in the compilation process. All right, so let's have some fun and implement our first macro. So on line 3, we've defined trace. And we know that we want to return a macro, accept a macro and return a macro. And with quote, we're going to generate that AST. So as kind of iterate over this, we're just going to simply implement the existing behavior of executing the expression that we passed to it. So here, we're using unquote, so we can inject the AST into the AST that we're creating. And the AST at this point will be our 3-element tuple. And in case of our add macro, it will be the X plus Y. Okay, so if we left it like that, that would be fine. Our expression would get returned as the AST. At runtime, that would get invoked. So we have no change in behavior. Okay, so next we want to do this thing where we're doing a tracing an expression and know what the expression is and the result and print that to standard out. So just to hard code that in, here's our string. You can see that we have our x plus y expression and returns 3. So obviously we don't want to leave that hard coded in there. Now the nice thing is that you can see that we have result and result, the result of that expression. And so we can replace 3 with result. So we can do some string interpolation here. Okay, now we have our x plus y, and we want to be able to do that dynamically. And so this brings us to toString on the macro module, and it allows us to convert the AST to a string. This is actually quite helpful if you're testing macros or debugging. And so now we can see using toString, we have that string. And again, we want to inject into the AST, into that quote, our source var. And so we replace that with unquote. So as a little bit of a sense, that's our completed macro. And so to have a little bit of a sense of completion here, let's invoke that at the command line. Okay, so at the REPL, we're going to invoke add, and as in the start of our presentation here, we get the expression that we're running and the result printed to standard out. And just to make sure we're not cheating, we're passing 3 here and 10 to get 13. And again, shows that the result is dynamic. And that, my friends, is the upside down dimension of Elixir. Again, to recap, I like to think that there's these 2 realities in Elixir: the human world, where we're writing our business logic that gets executed at runtime. We have some, we write in our high-level syntax in that business logic, and we are primarily writing functions. But in the upside down dimension, we're in the business of code generation, and that gets invoked at compile time. Our macros get invoked at compile time. And we have this internal data structure that we can manipulate. And rather than writing functions, we can write macros. So what's our next steps? Well, if you've really never checked out the generated web module for Phoenix, I think that's a good place to start. Sometimes, you know, the stuff gets generated and we might not exactly know how that's working. So that's, you know, that's a good place to go. You could also check out my repo, where I have these examples. I think it's great to sort of play around with this at the REPL to get a better understanding of it. Also, Chris McCord's book, Metaprogramming Elixir, is this wonderful 100-page dense, comprehensive guide to metaprogramming. It's certainly well worth checking out. Something I haven't listed here but comes to mind is the Elixir documentation for the macro module is very good, especially the documentation for quote that we looked at in our demos. And thank you very much for your time today. If you have any questions or comments, please reach out to me on Twitter, and please take care.
Thank you, Nicholas. That was a great talk. Thank you so much.